Greetings from Izmir's of Technology. We are Cengaver Rover. Our journey started at 2022 by just 4 people. Now in 2026, we have grown up to the 45 dedicated team members. After competing in ARC23 and ARC24, we are now fully focused on our next big goal, ARC26. To stay organized, we operate through 5 specialized sub-teams: mechanical, software, science, electronics, and management. And each team has subgroups to define roles to ensure every perfect detail of the rover. While we do our main development in our workshop, we take our testing to the fields. We use rocky and the rough terrains in our campus to put subsystems to test.
I'm the mechanical team lead. Mechanical team is divided into 3 sub-teams: mobility, manipulator, and science.
The rover's skeleton is a 710 by 310 mm rectangular aluminum T-slot extrusions, constructed from 6000 series. 6000 series selected for its optimal strength-to-weight ratio. Main chassis interfaces with the mobility system through a central shaft mechanism supported by precision bearings. Legs are connected to these shafts and constructed from aluminum box profiles, which is joined by custom sheet metal plates. The other tire is measuring 282 mm in diameter and 150 mm in width. It is additively manufactured from TPU95A filament. This tire integrates 2 distinct geometric patterns. First, the internal lattice is a re-enter honeycomb geometry to create an auxiliary structure with a negative Poisson's ratio. This lattice elastically compresses to absorb high frequency shocks, while the exterior chevron thread maximizes mechanical soil interlocking. Power is generated by an RS775 brushed DC motor paired with a 1-to-100 planetary gearbox to produce a high torque.
While designing our rocker suspension system, we were inspired by NASA's Perseverance rover. Yet, we developed the design to be lighter and leaner to ease the manufacturing process. We utilized the 6000 series aluminum alloy for the differential bar to ensure high rigidity and durability. To minimize weight without a significant strength loss, we improved our design by incorporating specialized cutout patterns into the differential bar. For the transmission system, we opted for fisheye bearings to provide flexibility and reduce wear caused by multidirectional stresses. Lastly, our analysis shows that even though the weight of the rover's body is completely shouldered by the suspension system, the weakest point can resist that load with a safety factor of more than 2.4. For regolith collection, we designed a closed rotating helical mechanism. The outer cylinder features helical canals with an optimized attack angle of 28 to 30 degrees. This ensures efficient material scooping while protecting the internal chamber from dust and mud. By applying specific parametric equations to the spiral design, we ensure that collected material is always centered during rotation. To seal the chamber, we utilize the 3-lug bayonet cap, which provides a more uniform load distribution compared to standard.
Our rover features a 5D robotic arm inspired by the Dexter arm, designed for high precision and high torque. It is built from 6000 series aluminum and it weighs 8.5 kilograms. It is able to lift 6.2 kilograms and has a 95 centimeter reach capacity. To reduce inertia, the wrist motor acts as a counterweight for the remote actuated elbow. The arm is driven by Neo 17 stepper motors with 100-to-1 gear reducers and utilizes a double loop encoder system for accurate, backlash-free autonomous control. A screw-driven gripper maximizes grip force, and the entire system is easily accessible for rapid field repairs. We define the desired end effector orientation and use inverse kinematics to control the robotic arm in task space. A screw-driven gripper maximizes grip force, and the entire system is easily accessible for rapid field repairs.
Our manipulator is controlled by a custom-designed 4-layer PCB based on STM32. It communicates with Jetson Orin Nano for command and sensor readings. The board drives 6-stepper motors using TMC2209 modules and magnetic rotary encoders.
Functions of the rover body is controlled by a custom-designed 4-layer PCB. The board drives 2-stepper motors for rotating 360-degree camera, drives the headlight, controls the indicator lights, runs the cooling fans, measures pressure, temperature, orientation, and battery voltage. We utilize an STM32 G4 series microcontroller capable of motor control. Inside the board, components communicate with the MCU using I2C and UART. The 3-color indicator light turns red when the rover is stopped, turns yellow when in autonomous mode, and turns green when manual operation mode.
The rover's power distribution system uses a dual relay switching architecture with 7 24 volts 10 amps fuse protected relays and reverse voltage protection. Any STM32 and 28 BGTs handle the safety logic, individually controlling power flow to the robotic arm, body board, science kit, and 4 DC motor drivers. The red mushroom e-stop button drives 2 relay coils in series via AND OR gate logic.
The wiring system is designed for maximum reliability and rapid field maintenance. We use industrial-grade M19 connectors for power and signal lines. This modular setup provides vibration and water resistance for powertrain and robotic arm connection. Type-C panel mounts handle high-speed data transfer for perception system that includes camera, LiDAR, and depth module, while an external XT60 port enables battery charging without opening the tablet.
The brain of our science kit PCB is the SP32. We choose it for modular design, allowing for easy replacement. For extra reliability, we added CAN bus support for emergency communication in case of wireless signal loss. Although the science kit runs on its own dedicated battery, we included a backup power input from the main rover battery to handle any local power failures. For mobility, we demand high torque for mechanical power and effective drilling. We are using 2 BTS 7960 motor drivers to control our dual RS775 tri-motors. For our specialized mechanism, we implemented TB6612FNG driver, which provides precise control over our KGP37 gear motor. For soil analysis, we rely on a dedicated pH sensor module to accurately measure sample mass and verify successful sample collection. We design a custom measurement circuit using a low cell period with an HX711 24-bit amplifier.
The rover uses differential drive control for traversal using 4 independent wheels. Each wheel is equipped with a brushed DC motor and an encoder used for velocity PID control. CAN-FT component is used inside the rover as it's very high speed, very reliable for electromagnetic interference, and very flexible through its bus topology. For outside communication with the ground, which allows us to transmit high amounts of data over long distances.
Our software team is divided into two subsections. One of them is simulation autonomy and the other one is user interface and control. Let's hear what each sub-team has done.
The simulation team handles sensor placement optimization, autonomous driving and object detection. By simulating different obstacle types before the physical race, we can improve our algorithms without risking damage to the rover.
For instance, we recently tested object mazes and slope scenarios to improve our obstacle avoidance logic. We can also manually control the simulation.
The control team handles connectivity analysis and efficient driving of the rover. Control management is done by using Foxglove framework. We use custom-built Foxglove panels in order to control properly our rover as we wish. We also make sure the rover responds as fast as possible to user commands, even with latency or interference. An example is our fail-safe system. If the connection drops, the rover automatically stops instead of drifting off course.
Our simulation and control sub-teams allow us to have both theoretically and physically accurate data. We also run Docker on all our code to ensure security and stability.
As the science team, our research is focused on Athabasca Vallis, one of the youngest and most scientifically significant regions on the Martian surface. Using JMARS for detailed surface analysis, we identified this site as an intersection of volcanic and high aqueous activity. This region is challenging for exploration and offers a remarkably fresh geological record. We try to adapt our science kit to the conditions we may face. Our aim is to identify the most recent hydrological history and potential subsurface ice deposits.
To investigate complex Martian environment, we have developed a science kit specialized for high-fidelity in situ analysis. Our focus is on identifying chemical and biological signatures that may exist within the Martian rocks and soils.
Our science kit is divided into two primary systems, the regolith collection kit and the drilling assembly. To the drill system, the assembly operates in 3 stages. We integrated a 35mm Forster bit to ensure clean holes. Directly behind the bit, a 30cm Archimedes screw handles the continuous vertical transport of collected samples and prevents the chance of struggling. Finally, to control the drill movement with high precision, we use an 8mm lead screw mechanism. This provides the necessary mechanical advantage to exert consistent pressure and adjust feed rates according to varying soil densities, ensuring the motor operates smoothly without stalling.
Seeking to improve our previous spectrometers, we conducted comparative tests with the Universal Lab spectrometers to verify that a visible to near-infrared spectrometer would meet our scientific goals. Our system targets K-spectral signatures on Mars analog surfaces, iron oxides and chlorophyll red edge as a bias signature. We are currently developing a spectrometer based on linear charge coupled device image sensor and a dual mirror optical path, covering a range from 400 to 1000 nanometers.
As a science team, we conducted several experiments to detect signs of life by testing for organic molecules. First, we used the Barrett test to check for peptide bonds. The color change from light blue to deep purple indicated the presence of proteins in our sample. Next, we performed the Benedict test to detect reducing sugars, and we observed a color change from blue to brick red, confirming their presence.
In addition, we used a nanodrop device, thanks to Akgül Lab, to detect DNA in our sample. Based on both our experiments and literature research, we concluded that detecting organic molecules is essential for identifying life. We aim to apply these methods in the field during the Anatolian Rover Challenge.